Okay, again, and so what I want to do is just one more example now to kind of complete what we're talking about with the differentials. And then after this, we'll make either a video or a pen cast about the second part. Remember I told you section 4.6 was going to have two parts to it. The first part was differentials, which is what we're talking about right now. And then the other part was linear approximations. And we'll talk about that in the next installment. But for now, one more example how we can use differentials. And this is just one of many, okay? Again, consider the following. Okay, let S of t be the position of an object moving in a straight line. Okay, so again, thinking back to the work that we did back in section 3.6, I think it was, okay? Okay, and let's suppose that we have a specific time interval. We'll say time equals a to b. Okay, so some specific time interval. So S of t is the position of an object moving over a straight line over a specific time interval. This is its velocity. And let's say that graphically it looks something like this. Okay, so what you see here again, this graph here represents the velocity function. And the time interval, like this, okay? Now, what I would like to do is I would like to calculate the area underneath of that velocity curve, okay? I want to find all of that area trapped between the velocity graph and the horizontal time axis, okay? So, like, why would we care about such a thing? It can be shown, and early physicists were able to determine, gang, that if you could calculate the area trapped between the graph of the velocity function and the horizontal time axis, that quantity and its area geometrically would correctly represent the displacement of the object over the same time interval, okay? But we'll leave that for a whole other discussion. For now, we just want to focus on trying to calculate the area trapped between the curve and the horizontal axis, the time axis, okay? So here's one clever way that we can do this using differentials, okay? Again, between A and B, between those two times, there are an infinite amount of times to choose from. Let's say right here. Okay, for that particular time. For that time, I can create what we refer to as a corresponding differential area. Now, why do I say differential? Well, remember, what did we say differential represents? Differential is a very, very tiny quantity. Okay, remember, it's very small. To the untrained eye, that probably looks like a line segment, like just a straight red line. But for us, we look at that and we say, you know what? That's a very, very thin rectangle. Okay, it's a very thin rectangle. And it touches the top of the graph right here. Okay, now is it a perfect rectangle? Well, no. The way that I fit it in here, so here's a blow up of it right here. Okay, so notice, gang, that the rectangle touches the curve right about that point. That's where I labeled it right here. Okay, and so I want to find the area of that one red rectangle. Okay, now it's very thin. It's a differential element, we called it. Let's say that the width of it is dt. Okay, again, using differentials now. So I appeal to you, gang, and what's the area of a rectangle, right? The length times the width. Well, what is the length of this rectangle, right? It's going to be its height. Its height is the y coordinate of this position right here, or this dot right here. Okay, right there where the corner is. And what is that y coordinate? Well, it's v of t. So I'm going to call the area of this rectangle, I'm going to call it dA. Okay, differential element of area. It's a very tiny quantity because it's so thin. And it's equal to the length of the rectangle times its width. okay? The length times its width, all right? Now, theoretically, gang, mindful that's a very, very thin rectangle, ask yourselves, how many rectangles could you theoretically fit in there if they're so differentially thin? If you guessed an infinite amount, then you guessed right, okay? And the idea is fill up that entire region with all of those little red rectangles. There's so many red rectangles in there, gang. They blend into each other. It looks like one solid red region, okay? So what I want to do is I want to sum up all those areas to get the total area, which is what we're looking for, okay? So we say that the total area is equal to the sum of all those elements. That's the letter S right there, okay? The sum of all those differential elements of area, okay? As they range, here's another way to write this. What does dA represent? It represents this quantity right here. As those rectangles range from time t equals A to time t equals B, okay? So that's the letter S, and it means sum up all those differential elements of area. They're very, very thin, right? But look at that. Isn't that very clever what we did? Now, we'll be doing a lot more of this. This was just to give you yet one more example of how we can use differentials in a practical sense in our calculus work. We'll see much more of this concept when we get to section 4.9, and then again, even more so when we get to chapter 5, because that's kind of like the centerpiece of chapter 5, as it turns out, okay? So let me just mention to you, this is sometimes referred to as a definite integral, but what does it represent? It represents the area trapped between the graph of the velocity function and the horizontal time axis. And what we'll see is, what does that represent in terms of physics, right? The geometry of it, I just told you what it was. In terms of physics, what it's going to represent is the displacement of the object. In other words, gang, its change in position relative to where it started, okay?